Hello everyone and welcome to our presentation. I am Malak Gherbi and now I'm presenting our research on combining sliding mode control and recurrent neural networks to optimize the performance of small wind turbines installed on electric vehicles. The aim is to improve energy efficiency by recovering wind energy during vehicle motion through a robust and adaptive control strategy that adjusts in real time. Our motivation lies in the environmental concerns tied to the transportation sector. EVs help reduce emissions, but they still depend on external charging sources. To enhance sustainability, we explore onboard wind energy harvesting using ram air turbines, which convert relative wind during motion into usable power. However, integrating a turbine into a vehicle isn't simple. It introduces aerodynamic and mechanical challenges that can affect performance. Our goal is to develop a system that maximizes energy recovery without compromising efficiency. From an aerodynamic perspective, the placement of the wind turbine is critical. To be effective, it must interact with areas of the vehicle where the airflow is smooth, high speed, and stable. Placing the wind turbine in regions with turbulence or flow separation can reduce its performance and increase drag. Basic aerodynamic guidelines suggest positions like the vehicle roof or rear edge, where airflow is more predictable. Though we haven't done CFD modeling yet, these considerations are essential for guiding our design feasibility. And now let's briefly go over the fundamentals of the wind turbine operation. Wind power is proportional to air density, rotor area, and the cube of wind speed, as shown in the power equation. Key performance parameters include the tip-speed ratio and power coefficient, both of which affect how efficiently the turbine captures energy. The aerodynamic torque plays a central role in driving the rotor, which we aim to control. Understanding these variables is crucial to setting control objectives and ensuring efficient power extraction.
Greetings everyone, my name is Khalid Al-Fuwail and now it is my turn to present. This diagrams illustrates the overall control architecture. At the core we have the recurrent neural network or the RNN that continuously estimates the uncertainty dynamics of the wind turbine. This information is fed into the sliding mode controller, which ensures that the turbine rotor operates at the optimal speed for maximum power extraction. And the key innovation here is the online updating algorithms of the RNN in real time, which allows the system to adapt to changes in wind and vehicle speed. Now let us look deeper into the neural network itself. First, the input layer filters the measured turbine speed and generated power to eliminate noise in the hidden layer. We use 6 neurons with the hyperbolic tangent activation function to capture nonlinear behaviors. And finally, the output layer generates a lumped uncertainty estimate that helps the controller to compensate for modeling errors and external disturbances. Now here we simulated the control system under elastic and profiles. This graphs, for example, here shows the uncertainty estimation. At the beginning there was a diverge and they come into converge as the time passes. Here we have plotted the power capture coefficient, blade pitch angle, and the tip ratio speed. And here we plotted the turbine speed and the motor rotor speed comparison. Of course, the difference here is due to the delay in the components, in the movement components, due to the friction and in the components of the wind turbine. And here we plotted the current, the q axis and the q axis and the d axis, and here we plotted the electromagnetic electricity and etc. Here is a zoomed in look at the power output over time. We can see that the proposed system is capable of maintaining a high power generation level despite varying wind speeds. The system adapts quickly, showing its robustness and effectiveness in real-time scenarios. And of course, compared to a typical vehicle mounted turbines, our system shows up to 4 times more power generated than this reference here. This reference here proposes the same approach but without the controller. And also the simulation reached a peak output of 1500 watts, and we achieved an optimal tip ratio speed of 7.5, which is an ideal for high efficiency. These results highlight the performance advantage of combining landing mode control with the RNN-based uncertainty estimation. And to summarize, our hybrid control strategy provides a robust power optimization for vehicle integrated wind turbines. The sliding mode control, for example, ensures the stability and the fast convergence, as we can see in the graph before, while the RNN adapts to uncertainty in the real time as the time passes. The result is a significant improvement in the power output, up to 4 times higher than the previous or the normal wind turbines, mounted up wind turbines, than some baseline system. In the future, we plan to implement this hardware and perform a real-world validation, including tests in the wind tunnels and moving vehicles, of course. At the end, I would like to acknowledge the Interdisciplinary Research Center for Renewable Energy and Sustainable Power Systems for their support, and with the grant that we received from National Industry Development and Logistics Program, all under King Fahd University of Petroleum and Minerals. And here are the references that we used, and we would like at the end to thank all of you for your listening, and questions are welcome. Thank you so much.